Let us now try to see if we can have a rigorous mechanism for testing for linearity. There is such a procedure and we call it the commutation diagram. This commutation diagram approach is simply a formalization of what we have already been doing. What we do is the following: we have a system and we wish to test whether the system is linear, and all we need to do is to check whether scaling operations and superposition operations when applied to the input actually are equivalent to the same scaling and superposition operations applied to the output. Let me explain this first by a block diagram. Let us first call both scaling and superposition operations by one common name. We call them linear operations. So, what I will now point out is that the property of linearity, if possessed by a system, is simply equivalent to commuting the linear operations with the system itself. So, suppose I start with x 1 of t or x of t. I first apply a scaling operation to it, a linear operation I will just represent by L, and take its output to the system itself. And I get some output over here which I will call say y t. Now, if the system is linear, then this output should be the same if I first pass the signal through the system, pass the input through the system and then apply the linear operation. That is to say that if I did this instead of the above, I should still get y t. Every system for which both these constructions that we have drawn here yield the same output, or every system which satisfies this, that the outputs are invariant to the order in which the linear operation and the system are applied, is a linear system. So, we are essentially going to have a mechanism to rigorously test whether the system does indeed remain invariant under an exchange of the linear operation, namely scaling or superposition, and the system itself. Let us now discuss the commutation diagram. Here we make the diagram as follows: to first test for scaling, that is to test for homogeneity. Let us apply x t and pass it through the system. It produces some output y t. Instead, we could also apply a scaling operation to x t, scaling by a factor a, for example, to get a times x t, and we could see what output arises if a times x t is fed to the system. If x t yields y t, what does a x t give us? And on the other side, we have y t already here, and we can apply the same scaling operation, that is multiplication by a, to y t. So, we would get here something else, we would get a times y t in this place. Now, the question is what we will get in this place where a x t is applied to the input. If here also we get a y t, then the system is homogeneous. A similar thing is done for superposition. What we will do is the following: apply, consider two signals x 1 t, x 2 t, apply both of them to the system one after the other or whatever, to get the corresponding outputs y 1 t and y 2 t. Now, if these two signals applied at the input x 1 t and x 2 t are added to each other, we would get x 1 t plus x 2 t. What we will do, of course, is as with the test for homogeneity, we will apply this combined signal x 1 t plus x 2 t to the same system and see what we get as the output. Here, of course, we will on the other side add y 1 t and y 2 t to get y 1 t plus y 2 t. If x 1 t and x 2 t added together to give x 1 t plus x 2 t, that signal is applied to the input, then if the output is again equal to y 1 t plus y 2 t, then this system is linear. In short, this system is additive. In short, let us put it this way: the commutation diagram takes you from the input to the output in two different routes. In one route, you apply the system first and the linear operation later, in this case addition. So, you apply the system first and then the linear operation and check the output. Compare that with the other path through the commutation diagram, where you first apply the linear operation and then apply the system. If the end result is the same irrespective of the two paths, that is when you would say that the system commutes with that particular linear operation, namely addition in this case. So, if you test whether the system commutes with addition as well as test if the system commutes with scaling of the input, then together we have succeeded in showing that the system is both homogeneous and additive and therefore linear. Let us work out a few examples using the commutation diagram, and that will help us understand how to use this diagram. So, let us take an example like y t equals 2x dot t, let us say, by which I mean 2 dxt by dt. Let us say the system is a differentiator and also scales the input by a factor of 2. So, this is our system. We wish to check whether the system is linear, and we will do it by first testing for scaling to see if the system is homogeneous. So, apply a scaling operator to the input and see if the system commutes with the scaling operator. Let us have x t over here and we make the commutation diagram. The output for x t is y t equals 2 d x t by dt. On this side, we apply the scaling operator first to get a times x t, and we wish to see what happens if a times x t is applied to the system. If a times x t is applied to the system and the system is a straightforward differentiator, then we know that the output will be 2 a dxt by dt. This is what we get by coming through this path of applying the linear operation first and then the system. Now, through this other path we have already seen the output, and we will apply the same linear operation on the output. We have 2 dxt by dt, and if we scale this by a factor a, this will yield us a times 2 dxt by dt. Clearly, these two are equal to each other, and therefore, we have just seen that this system is commuting with the scaling operation by a. So, this system is homogeneous. Now, let us see about superposition. Let us have x 1 t plus x 2 t as the input. The system's output would be y 1 t plus y 2 t, which is 2 d, excuse me, initially we have not yet added the things. So, we just have x 1 t and x 2 t being applied to the input. That would give us 2 d x 1 t as the output for the first signal, 2 d x 1 t by dt, and 2 d x 2 t by dt as the other output. So, for this pair of inputs we get this pair of outputs separately. Now, let us see what happens when we add this pair of inputs. We would of course get the combined input x 1 t plus x 2 t as the combined input. Now, there are two things to do. First, check the output when the input is x 1 t plus x 2 t. That is very straightforward, because we know what the system does. The system differentiates the input and scales this result by a factor of 2. So, what we have now is 2 times the time derivative of x 1 t plus x 2 t, which is d by dt of x 1 t plus x 2 t. This is what we get going by this path of adding first and applying the system later. Now, let us see what we get by this path, where we have already applied the system to get the two respective outputs, y 1 t equal to 2 d x 1 t by dt and y 2 t equal to 2 d x 2 t by dt. We just add the two. Now, when we add the two, we would just get 2 d x 1 t by dt plus 2 d x 2 t by dt. These two are obviously equal to each other. So, the system has shown itself to be additive, because addition is commuting with the system. So, collecting these two things together, we can say the system is homogeneous as well as additive. Therefore, linear. That is it. Now, one more example. This time let us pick something which we suspect at least to be nonlinear. Okay. So, let us take y t equals say tan inverse of x t. The tan inverse function is, I think, known to all of us to be nonlinear, but let us see what happens when we apply the commutation diagram. First, for scaling, we have x t, you get y t equals tan inverse of x t. Here we scale x t by a factor a to get a times x t and apply the system to get tan inverse A x t. From the other side, we would get, we will have to scale the output by a factor a, and so we would get a times tan inverse x t. Now, it is well known to all of us that tan inverse a times x t is not the same as a times as tan inverse a x t. So, these two quantities are not equal to each other. So, the system is not homogeneous. Let us see about the additivity. You have x 1 t plus comma x 1 t comma x 2 t as the two inputs, and the corresponding outputs would be tan inverse x 1 t tan inverse x 2 t. Those would be the corresponding outputs. Now, we have to add these two inputs to get x 1 t plus x 2 t on the one side. Apply the system to x 1 t plus x 2 t, you would get tan inverse x 1 t plus x 2 t together. Whereas, if you already take the two outputs tan inverse x 1 t and tan inverse x 2 t, you would simply add the two over here and get tan inverse x 1 t plus tan inverse x 2 t, and certainly these two quantities are not equal to each other. So, it is not additive. The system is therefore not linear. We could work out any number of examples on this principle, but let me just work out one last slightly tricky example. Suppose we say that y t equals x t divided by x 0. Is this system linear? We want to know if the output is such that the system's homogeneity and additivity can be demonstrated. Now, look at this expression carefully. There can be a problem here, because this definition of a system itself is suspect. The problem is that if x t or rather x 0 were equal to 0, then we will have to make a fresh stipulation. Let us say if x 0 equals 0, then y t equals say x t itself. Now, let us see what happens to this. Is the system homogeneous? Let us just understand what I have written over here. I have taken x t, applied it to the system to get x t by x 0. If I scale x t by a factor a as I have done on this side, then a x t is the input, and when a x t is the input, the corresponding output by the definition of the system should be a x t by a x 0, which is just equal to x t by x 0. Now, let us see what happens on the other hand if I scale the output of the system obtained directly before scaling, that is x t by x 0 by a factor a. I would get a times x t by x 0. So, through one path I have got a times x t by x 0, through the other path where the scale operation, the linear operation preceded the system, we have got x t by x 0. Now, these two things are definitely not equal to each other. There is no doubt that the system is not homogeneous for all signals where x 0 is non-zero, because wherever x 0 is non-zero, this is what we would be writing. Now, if x 0 over 0, then what happens? If x 0 happens to be 0, that is, of the set of all signals in this world, separate this set into two parts: those signals which have x 0 equal to 0 and those signals for which x 0 is non-zero. We have just completed our exercise for only homogeneity for the case of systems where x 0 is non-zero. For that category of signals taken as inputs, we have found that the system is not homogeneous. Now, if we consider the other class of signals, the class where x 0 is 0, then what do you think will happen? Then we will just make modifications in this very diagram. Okay, let us draw a fresh diagram. If x 0 is 0, then we have y t equals x t, and we know the system to be linear. Is in fact linear. So, it is also homogeneous. So, there is no problem when x 0 is 0. There is, however, a problem, as we just demonstrated earlier, when the system is impressed with a signal for which x 0 is non-zero, because then this definition would come into play. Now, it is really not necessary to test for homogeneity here, but let us do it anyway. It takes only a moment to test for additivity. You have x 1 t plus x 1 t and x 2 t being applied simultaneously to the input, or one after the other, so to speak, in parallel to get the outputs x 1 t by x 0, y 1 t x 2 t by x 1 0 and this is x 2 of 0. These are the two respective outputs. Now, if you added the two inputs, we would get x 1 t plus x 2 t, and what would the output be under this circumstance? It would be x 1 t plus x 2 t divided by x 1 0 plus x 2 0. whereas if we just added the two outputs, we would get x 1 t by x 1 0 plus x 2 t by x 2 0. Now, these two are definitely not equal to each other. So, again for signals where x 0 is non-zero, the system has proved to be non-additive, it is not additive, just like it was also not homogeneous. Going back to the instance where we consider signals for having x 0 equal to 0, then the definition of the system changes to y t equals x t, and that system is also additive, just like it is also homogeneous, the whole system is linear. So, let us summarize what we have learnt in this example. For this example, we find the system is linear for some signals, namely those for which x 0 equals 0. For such input signals for which x 0 equals 0, the system is linear. The system, on the other hand, is not linear for other signals. Namely, those for which x 0 is non-zero. So, now what happens? How do we declare the system? Do we declare it to be linear or not linear? This brings us back in fact to a very important statement that we have been making every time we make any of these definitions of properties of systems. A system is said to have a property like linearity or causality or stability, whatever we have discussed so far, only when that property is valid for every input signal. Using that principle over here and recognizing that this property of linearity is not available for all input signals, only for certain input signals, we will therefore say that the system is non-linear or not linear. Let me summarize what was very special about this particular example. This is the first example that we have considered so far, where the system behaves with different properties, exhibits very different properties depending upon which signal is applied. For certain signals it shows linearity properties, for certain signals it does not exhibit linear properties. And for a situation like this, as I have said, we will have to go by the principle that unless that property that we are testing for, such as linearity, is available for every input signal, we will not declare the entire system to be linear. We will say in fact that the system has failed the linearity test, that the system is not linear. This example is therefore a little unusual. Let us now move on to the next property of systems, next important property of systems, which we shall call time invariance. every time I introduce a new property, I make some comments about whether it is a domain related property or a range related property. Thus, causality, memory were all domain related properties, and stability, linearity were range related properties. Now, we have come to this fifth property, which we call time invariance, and we would perhaps like to ask the same question: is this a domain related property or a range related property? And the fact is that this is also a domain related property. What is time invariance? Time invariance is again a phenomenon that we would like to see in a lot of real world systems around us. Time invariance is one form of consistency. Of course, linearity was also a form of consistency, in that we expected the system to be invariant to scaling and superposition. Time invariance is a different kind of invariance. It is invariance with respect to translation of the input signal on the time axis. In short, what we expect is that if we time shift an input signal and apply it to the system, then the output that we get must be the corresponding time shifted version of the original output. If x t yields a certain output y t, and if the system is time invariant, then x of t minus t naught, which is a time shifted version of x t. We have already discussed what happens to the signal when it is given a time shift or a time translation. We know how the signal changes. What we want the system to do, however, is to ensure that when x t minus t naught is applied to the system, the output is y t minus t naught. This, we must understand, is also a kind of commutation. If we consider this operation of time shifting to be another kind of transformation we apply on the signal, that is, if we can say that time shift itself is a system in the following sense, that we have a system which takes x t as the input and produces x t minus t naught as the output, which I will call the time shifting system. Time shifter, okay, and I will denote it by say T s time shifter by the amount T naught. Then this is a system now. So, I could alternately write this expression as x t applied to T s of time shift of T naught gives x of t minus t naught. So, I have made a system out of it, just like in my discussion of linearity, I made a system out of it when I said that a linear operation, be it scaling, be it superposition, will be treated also as a system, put it in a box. Now, what we expect of time invariance, or what we understand from time invariance, is the following. If I have x t and apply it to T s of T naught, then apply it to the output of this T s of T naught to the system, I get an output which I will just call y t for now. The alternative thing to do is to exchange these two systems in the order of application. To get x t applied to the system first, then applied to the output of the system T s by of T naught. This is the second manner in which we can apply the two systems on x t, first the system then T s by T naught. Earlier we did T s by T naught, T s of T naught and then the system. The output we get here must be the same as before. Y t in both cases must be the same irrespective of which of these two is applied first, and that therefore makes the approach to understanding time invariance very similar to our approach of understanding linearity. We could again in fact use the commutation diagram. Now, unlike last time where I examined systems first, examples of linear and nonlinear systems, tried to find out if linearity was upheld or not, I will directly start evaluating examples using the commutation diagram. However, this commutation diagram will work with time invariance rather than with linearity. So, let us take examples. Suppose y t equals k times x t, then x t is applied to the system as last time to get k times x t as the output. That is the first part of the commutation diagram, the first leg of the commutation diagram. The second thing is to apply the time shift operator to x t. If I did that, I would just write this as T naught over here. I would get x t minus T naught. Now, on x t minus T naught, I will again apply the system. What does the system do? It just scales the signal by k, and so it should do the same for x t minus T naught as well. I would get k times x t minus T naught. On the other hand, I already have the output of the original signal k x t, and if I applied a time shift to k x t, what would I get? I would get k x t minus T naught once again. In this approach, I would replace all occurrences of t by t minus T naught. That is what I would do whenever I time shift a signal. Wherever there is t, replace it by t minus T naught. That is what gives you the output. Now, you see that both these outputs coincide, they are the same, and this demonstrates that this system is time invariant. Let us take a slightly more interesting example. Suppose we have x t and the system produces t times x t, that is the output. Now, is this system time invariant? We want to examine what happens when we apply time invariance, the test of time invariance to this system. We have here x t applied to the system, we get t x t. Apply the T naught shift operator to it, we would get x t minus T naught. Now, apply the system to it. What would we get? Let us take a second example. Let us say that y t is equal to t times x t. So, is this system time invariant? It will turn out that it is not time invariant, but we can see that by using the commutation diagram. We have x t, and applying x t to the system gives us t x t according to the system. Now, alternately, if we first apply the time shift of t naught, we would get x t minus t naught. Now, let us see what happens. We have to be a little careful here, because it is very easy to go wrong. I keep going wrong very often. We have here t x t as the output already produced when the input was x t. Now, what happens when you time shift a signal t x t? When you time shift a signal by t naught, you have to replace every occurrence of t by t minus t naught. And so, if t x t is subjected to a time shift of t naught, the output would be t minus t naught x t minus t naught. So, that is what we would get if we time shifted the output signal, the output of the original signal. Original signal is x t, applied through the system we get t x t, time shifted we get t minus t naught x t minus t naught. On the other hand, if we apply the time shift to x t directly, we get x t minus t naught. This is just some other signal, you could call it x dash t if you liked. Now, if x dash t or x t minus t naught is subjected to the system, we ought to get t x dash t, because that is what the system does. The system multiplies the input by t. So, what is t x dash t? That is equal to t times x t minus t naught. So, through one path in the commutation figure, commutation diagram, we get t x t minus t naught. This happens when you time shift first and apply the system next. Through the other path, you have the system applied first to give t x t, and then the time shift applied to t x t to get t minus t naught x t minus t naught. The expressions are completely different, as you can see, and these two systems are not equal to each other. So, this system is not time invariant. We would simply say the system is time varying. Let us take yet another example of a system which gives rise to a different transformation on the signal, a transformation that is of the third kind that we discussed when we discussed domain transformations, time dilation. So, if x t is applied to the signal, let the output be x of 2 t. This means the signal has been shrunk along the time axis. You can go back to the previous lectures and look at the diagrams, you will see what is the difference. So, you have x t applied to the input and x 2 t are coming out as the output. Now, let us apply the commutation diagram. The point is that whenever we apply the commutation diagram to time invariance, it is a very common feature to make mistakes. So, we have to be very careful. X t applied to the system, you get x 2 t. Let us make a diagram also here to help us understand it better. Suppose this is x t, say minus 1 to plus 1, let us say this is x t. Then x 2 t will be of this form, it is speeded up. So, it is compressed in time. So, you just get from minus half to plus half. This is what we have on here. We time shift x t by t naught. Let us say t naught is some amount. To get x t minus t naught, let us have a diagram for this. Let us say t naught is positive, let us say t naught is equal to 1. So, that the output is sketched as, and it runs from 0 to 3 with its peak 0 to 2 with its peak at 1. This is the time shifted signal. Now, what happens if we time compress, or what we have called as dilation, if we apply the system to this x t minus t naught? X t minus t naught when dilated will give us this signal. It is easier to not go wrong with diagrams. So, we would get a signal which is compressed in the time axis. We would get where the signal runs from 0 to 1 only, and the peak is at half. So, this is the signal we would get. On the other path, we have this signal already given to us x 2 t, and we just have to apply a time shift of t naught equal to 1 to this system, to this input, to this output signal, and when we did that, we would just get this starts at minus half and ends at plus half. The support starts at minus half and ends at plus half. With a time shift of unity, it would start at half and end at 1.5. So, you would have this signal. Sorry, that is a little larger than life. From half to 3 by 2. Now, clearly these two signals are not equal to each other. The signal that arose from going through this path, where we delayed first and applied the system later, is this signal, which has a support from 0 to 1. The signal we get by first applying the system and then applying the time delay runs with a support from plus half to plus 3 by 2, and so there is a difference between these two signals. So, what are the expressions for these two signals? That is the next question. This signal, the one which we get by applying the time delay to x of 2 t, would be x of 2 t minus t naught. You can verify this by checking for salient points on this graph. For example, in this original graph of x 2 t, we have the peak occurring at 0, and here we have the peak occurring at 1. Let us just verify if that is the right answer. The peak is at 0 here, and we are carrying out a delay of 2 t minus t naught, 2 t minus 2 t naught. So, the peak should occur at 2 t minus 2 t naught equal to 0, that is where the argument of x t is 0, and that means that 2 t minus 2 t naught equals 0, or the peak should occur at t equal to t naught, which is equal to 1. That is what is happening over here. We can see that the peak is indeed occurring at 1. On the other hand, if we come through this branch, we have x t minus t naught already available here as the time shifted version of the input. Now, here we apply the system after the delay of t naught. So, what we will get here is x of 2 t minus t naught, and if this occurs at x of 2 t minus t naught, you can again verify that this diagram is the correct one by looking for the position of the peak. The peak should occur where the argument of x is 0. So, where 2 t minus t naught is 0, or where T naught equals where T naught by 2 equals T, that is at the point of time T naught being 1, there is a point of time where T equals half 1 by 2, and that is what is happening over here. So, this has an expression of x of 2 t minus T naught, this has an expression of x of 2 times T minus T naught. These two expressions also clearly are not equal to each other. This system is therefore time varying. I have no place to write it, but you can note that down. So, this is another time varying, this is a time varying system. You will find that since this is a domain related transformation, time invariance is not usually to be faulted whenever the system only involves domain range operations of the signal. For example, take y t equals mod x t. Now, taking the absolute value of a signal is a range operation on the signal. So, such a system should naturally be expected to be time invariant, and we can verify this very easily using the time commutation diagram. Once again, we have x t, and x t when applied to the system gives us mod x t. The time delayed version of x t is x of t minus t naught. Apply the system to it, the system finds its absolute value of x t minus t naught. That is it. Now, coming through the other path, we have mod x t, and here applying a delay is equivalent to replacing every occurrence of t by t minus t naught. So, that you get mod x t minus t naught, exactly the same as before. So, this is time invariant. So, these have been a few examples of systems which are time invariant and time varying. Now, what is the fundamental significance of time invariance? Time invariance, as I said, is another form of consistency. And what kind of consistency is this? It is the sort of consistency that physicists expect from physical laws. For example, if you slide a cylinder down an inclined plane, if you roll a cylinder down an inclined plane, you would get some particular acceleration and velocity for the cylinder by the time it reaches the bottom of the inclined plane. This is some sort of a physical experiment. Now, a physicist would certainly expect that you get the same results for that particular experiment, irrespective of which day of the week you carried out the experiment. In short, every physical experiment is carried out in the real world, which is largely believed to be time invariant with respect to the physical laws that we understand the world in terms of, and therefore, physical laws are said to apply not only at every place in the world, but also at every time, that they are valid for all time. Now, this is a deeper question, as many professional physicists will tell you, but this is the layman's understanding of a physical law, that the law should be verified irrespective of when you carry out the experiment to verify the law. The results should be same. If you carry out an experiment today, you get a certain set of results today. If you carry out that same experiment tomorrow, you should get that same set of results, not today, but tomorrow. So, whenever you carry out the experiment, you get the corresponding results at the time that follows the experiment itself. That is time invariance. It is a most straightforward thing, most natural thing, and something that you would expect from almost any physical system. However, in real life, things do change with time. There are gradual changes which have to be accounted for when we consider a system at the engineering level. For example, semiconductor devices gradually deteriorate with age. So, if you have, say, an audio amplifier made out of solid state devices today, its performance will not be the same if you used it daily for the next 50 years and tried and tested its performance at the end of 50 years. It would certainly be expected to be slightly inferior. This happens because these semiconductor devices, their behavior rather is not really time invariant. It does change with time, very very slowly, perhaps very very gradually, but it does change with time. A capacitor, for example, most capacitors are known to have gradual deterioration in their dielectrics. So, as time passes, the dielectric constant of the capacitor comes down. So, for the same voltage, the same capacitor will store less and less charge as it gets older. So, after a long time, you would probably find that the circuit, any electronic circuit, begins to malfunction because its components age. So, this aging is one manifestation of time varying behavior. That is true with human beings as well. If I gave this same lecture 40 years hence, I would probably not be able to even stand up. So, everything ages with time, and in that sense, if you look very closely, perhaps not everything in this world is time invariant. We do expect physical laws to be time invariant, because we are not expecting the world to age, the universe to age in the same sense that human beings age or electronic devices age, but maybe even the world is aging, we do not know. So, this completes the list of 5 properties of systems with respect to which we try to understand our systems, and in some sense this also completes one module, the first module of this course, where we have gone through the following steps. We have had an introduction, to the subject, we have had a discussion of what is a signal, discrete, continuous time, examples, etc., systems, introduction. Then of course, we went through lots of discussion on different kinds of signals. We discussed exponential signals in detail, unit step, unit ramp, etc., in detail. Then we talked about various transformations on time signals. And finally, we have spoken of properties of systems. This discussion, being preliminary, was also extremely general. We discussed all kinds of systems, we discussed all kinds of signals, because our objective was to make the study as general as possible. From this very very general setting, we will now progress towards a more constrained situation, where not all kinds of systems are discussed, but only systems that possess certain very desirable properties.